Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss electromagnetic induction as Faraday's law of electromagnetic induction, Lenz's law. Let's begin. What is electromagnetic induction? Look here, when a current carrying conductor produces a magnetic field, that particular phenomenon create an idea, can we reverse that process? Means, is it possible to get current from magnetic field? That type of question generates a new phenomenon that is known as electromagnetic induction. Means the production of an EMF in the coil due to the change in magnetic flux linked with it, that is known as electromagnetic induction. Electric current from magnetic field. That phenomenon was first of all observed by the scientist Michael Faraday. So, he proposed two laws regarding electromagnetic induction named as Faraday's law of electromagnetic induction. First law gives how exactly the EMF is induced or the cause of produced EMF, and second law gives the magnitude of that produced EMF, or we can say the magnitude of that induced EMF, and the direction of that induced EMF is referred by Lenz's law. So, we discuss these laws one by one. Faraday's law of electromagnetic induction, first law: whenever there is a change in magnetic flux linked with a circuit, an EMF is induced. Consequently, a current is induced in that of circuit. As the EMF induced, therefore current will be induced. It lasts as long as change in the magnetic flux continues. As long as magnetic flux changes occurred, as long as the EMF will be produced. Look here, if that be the coil, so here needed change in magnetic flux, therefore magnetic lines are required. If I take a magnet here, south pole and north pole, the magnetic lines of forces are there. The change in magnetic flux is occurred, either I change that magnet from this direction to that direction, therefore magnetic flux changed linked to that of particular coil, or I can change that coil from this direction to that direction. Again I can rotate that coil, that also the change in magnetic flux occurred here. So, in this way induced EMF or induced current is produced. So, what be the magnitude of that of induced current? The magnitude of induced EMF E is directly proportional to the rate of change of magnetic flux linked with that of circuit. That is, the induced EMF E is directly proportional to the rate of change of magnetic flux d phi by dt, rate of change of magnetic flux linked with that of circuit. Here we use the proportionality constant as k d phi by dt. The value of k is 1, therefore, E is equal to minus d phi by dt. The negative sign indicates the induced EMF is opposite to its production, to the cause of its production. So, that can be gives the direction of that induced EMF that is studied in case of Lenz's law. In Lenz's law, which gives the direction of induced current in that of circuit. What is the direction of that of induced current in that of circuit? So, the direction of induced current in such that it always opposes the cause of its production. The direction is opposite to the cause of its production. Let we understand it taking some experimental verification to that Lenz's law. Look here. Let we take a solenoid PQ, a solenoid PQ is connected to a sensitive galvanometer G and a magnet having north pole near the upper end of that of P and is moved towards the solenoid. Here the galvanometer shows a sudden deflection to right of 0, means an induced EMF is produced here or induced current is produced. This means that upper end P of that of solenoid acquires a north polarity. Look here, there will be the magnetic lines of forces linked with that of coil, linked with that of circuit. Due to this movement, there will be change in magnetic flux associated with that of circuits. So, here the opposite sense of that of north pole, there will be the south polarity. So, here north polarity is developed here, means the repulsion takes place. It opposes due to repulsion the downward motion of the bar magnet, which is cause of induced current in that of coil. Okay. Similarly, when the north pole, look here, that is the solenoid PQ connected with that of sensitive galvanometer G. Here a bar magnet, north pole near point P means the upper end and south pole far away, and that magnet is taken in this direction. So, there will be the change in magnetic flux occurred here. In that case, what happened? When the north pole of the coil is moved away from that of solenoid, the deflection in the galvanometer is reversed. That is, it is found to be towards the left from 0, left of that of 0. Here it is right of 0, that is left of 0. Here the galvanometer left of 0, here the galvanometer right of 0. This indicates that the upper end of that of solenoid acquires south polarity from the viewpoint of that of magnet. Due to the attraction, north south attraction, the solenoid opposes the upward motion of that of north pole of the bar magnet, which is the cause of that of induced current. Okay. So, from these two results we come into the conclusion that the induced currents are produced in such a direction which gives rise to such polarities at point P that oppose the moment of that magnet, which is very cause of production of that induced current. So, Lenz's law gives the direction of that induced current in that of circuit, which is taken as the direction of induced current in such that it always opposes the cause of its production. Okay. This is all about electromagnetic induction, Faraday's law of electromagnetic induction. First law, the cause of electromagnetic induced current. Second law, its magnitude. Lenz's law gives the direction of that of induced current. Now, derivation of Faraday's law. Faraday's law of electromagnetic induction we can derive by using Lorenz equation on a free charge. When a free charge moves in an uniform magnetic field, a force experienced with that free charge, and that force is known as the Lorenz force. So, here we take the bar PQ, R, S. Here a galvanometer is connected, G. These are the direction of magnetic field, that cross sign indicates these are the inverse magnetic field B. Here a conductor PQ means there will be free charge inside that of conductor PQ. We consider any arbitrary charge carriers having let charge Q, charge Q in that of conductor PQ. When that rod PQ moves towards left with the velocity v, then that charge q will also be moving with velocity v. So, here Lorenz force will be experienced, and that magnitude of Lorenz force, here the magnitude of Lorenz force is given by F is equal to Q V cross B magnitude. So, V cross B, the direction of B and V are perpendicular with each other. So, sin 90 will be 1. So, Q V B with the force experienced on that of charge Q, and the direction of that of force is given by Fleming's left hand rule, and its direction is from Fleming's left hand rule. That is towards Q, towards Q. Look here, this is the direction of magnetic field. That will be the direction of velocity. So, the force in the direction of Q, towards Q. Now, the work done in moving all the charge carriers from point P to Q. Therefore, the work done in moving all the charge carriers, since we take PQ as a conductor, there will be so many charge carriers. As you take one of the charge carrier Q, and the force experienced is given by that equation. So, the work done in moving all the charge carriers from P to Q, P to Q is, that is work done W is equal to, that is force on that charge Q and displacement, that will be the force on charge Q into displacement, the length of PQ. Look here, the length of that conductor Q is small l, and that one is at a distance of x from that segment. Okay. Force Q V B, Q V B, length of PQ L, that will be the work done. Since EMF is the work done per unit charge, since EMF is equal to work done per unit charge, therefore, EMF E is equal to work done per unit charge Q V B L divided by unit charge Q. Q cancel out, EMF E is equal to V B L. Now, V be the velocity, as velocity V is equal to rate of change of displacement, it is dx by dt, rate of change of displacement dx by dt. So, in place of V I can substitute dx by dt, or is equal to dx by dt be L, or is equal to B, look here, d by dt of Lx, length into distance, that be the area. Therefore, L into x is equal to A, that is the area, or E is equal to B dA by dt, or E is equal to d by dt of B into A, or E is equal to, this is the magnetic field into area, magnetic flux, magnetic field into area, that is the magnetic flux associated with that particular area. So, E is equal to d phi by dt, that is negative d phi by dt, that is proved, or we derive, that be the Faraday's second law of electromagnetic induction. The negative sign show the direction of that of produced EMF. In this way, we derive Faraday's second law of electromagnetic induction. Now, the integral and differential form of Faraday's law can be derived. Let us consider a loop of wire. Consider a loop of wire having the cross sectional area A, that is the wire, A be the cross sectional area of that wire, that is placed in a uniform magnetic field having magnetic field strength B, here current flow in this direction. Okay. So, the magnetic flux linked with the loop, the magnetic flux linked with this loop, that is phi is equal to surface integration of a B dot dA, B dot dA, the surface integral, the magnetic flux associated with that of loop. Now, differentiating that above equation with respect to time. Now, differentiating above equation with respect to time, we get d phi by dt is equal to that is d by dt of B dot dA. Okay. Area integration. Now, according to Faraday's law of electromagnetic induction, from Faraday's law of electromagnetic induction, the induced EMF is equal to minus d phi by dt. Therefore, the value of d phi by dt is put here, that is minus del by dt area integration b dot dA, that one. Now, from the definition of induced EMF, now take it as equation number 1. Definition of induced EMF is equal to, see the line integral of E dot dl electric field to that of closed curve from 1 and 2, where E be the electric field intensity. From 1 and 2, from equation 1 and 2, we get closed line integral of E dot dl is equal to minus del by del t area integration of b dot dA, that one. The integral form of Faraday's law, that is the Faraday's law in integral form. Now, here we can use Stokes' law to convert that line integral to surface integral using Stokes' law. Stokes' theorem. So, the line integral E dot dl can be written as the surface integral curl of that particular vector grad cross E dot dA. Therefore, that equation is written as, in place of E dot dl we can substitute that value. So, the area integral or surface integral grad cross E dot dA is equal to minus del by del t of area integral b dot dA. Okay, or I can write the area integral grad cross E dot dA is equal to minus area integral del b by del t dot dA. From these two sides equating, we have grad cross E will be negative of del b by del t. That equation is the Faraday's law in differential form. Faraday's law in differential form. Of electromagnetic induction, and that equation is also called Maxwell's first equation in electromagnetic theory, that is further named as Maxwell's first equation in EMT, electromagnetic theory. So, here we take integral and differential form of Faraday's law. Faraday's law in integral form, Faraday's law in differential form, or we can say Maxwell's first equation in electromagnetic theory. So, with the help of this video lecture, we understand electromagnetic induction, Faraday's law of electromagnetic induction, first law, second law, LENZ'S law, derivation of Faraday's law, integral and differential form of Faraday's law, differential form of Faraday's law. So, with this useful and informative notes, let me wind up this session. Thank you.